Hey everybody, welcome back to our video on Kalman Filtering. We're going to continue with our playlist of heuristic introduction to Kalman Filtering by considering the third major topic, and that is prediction. The prediction step is also known as the extrapolation step, and this is the part where the prediction is brought forward in time from the previous time step. In the running average example that we looked at before, the dynamics were quite trivial. The state didn't change at all. X at time k plus 1 was assumed to be the same as the state at time x of k. We just didn't know what the exact value was, and that's why we had to estimate it using measurements. So that example that we looked at before used a measurement of a resistor with a voltmeter, and we just did those measurements over and over again, and we didn't worry about the state dynamics because we assumed they weren't changing. In today's video, we're going to talk a lot more about the prediction step. So the prediction step takes the state estimate at time k minus 1 and brings it forward using a mathematical model to what we expect it to be at time k, the present time. That will give us the state estimate x hat with a little minus sign at time k. So in more general Kalman filtering, in order to do this extrapolation, we have to take into account a few more elements. So as I mentioned, we have to take into account the non-trivial state dynamics themselves, and that will be represented by a mathematical model relating the various state vector variable elements together. But there might also be time dependence. So it could be a function of the time explicitly. And moreover, there could be a forcing function like process noise. And that's what we're going to be talking about today, those key elements. Often the process noise is considered to be additive, so the dynamic function is considered to be only a function of time, possibly, and the previous state at time k. And then the white noise, if you will, the noise is just added in. If we wrote it a different way so that we're concerned with the state at the current time and extrapolating from the previous time k minus 1, then it would look like this last equation. For continuous time systems, we use differential equations. And so we have x dot being equal to some function, perhaps explicitly of the time t, the state at time t, and the noise as well. The dot over the state variable represents the derivative of x with respect to time. The form of the function f could be simple, or it could be very complicated. It could be linear or it could be nonlinear. Kalman filtering generally requires some kind of linearization. If you're dealing with a nonlinear dynamics, you're going to have to linearize it. And we'll get to that when we talk about various kinds of Kalman filtering, like extended Kalman filtering. The independent variable indicates possible explicit time dependence. And as we mentioned before, the process noise is assumed to be Gaussian white noise. We're not going to get into what exactly that means too much. We'll talk about it a little bit, but much more detail much later on in other playlists. General Kalman filtering also further complicates things by allowing the state variable to be vector valued. So f thus becomes a vector valued function, and it's often a matrix that multiplies the state, and possibly time dependent matrix. The process noise itself, in order to be, say, additive, would have to be of the same dimension as the state variable, so we typically have a vector valued noise process as well. So here's some examples of scalar dynamical system functions, f. In this case, we're going to assume that the system is continuous in time. It's time invariant, so it's not explicitly dependent on the time variable t. And of course, the function is differentiable over some bounded time interval from 0 to big T. So here's an example. It would be x dot at time t would be some function of x at time t and the noise at time t. And in this case, the example says that this function is identically 0. It never changes, okay? If the initial condition is a random variable, then this would be called a random constant function because we get a different value for x every time we integrated this using a different random initial condition. If, in fact, the rate of change of x is equal to its value at that time t plus some random noise, then this is an example of what we call a continuous random walk. And if it's equal to some factor minus beta times the previous time, or times the state value at time t, plus noise, then this is what we would call an exponentially correlated random process. We'll get into these in a lot more detail later, just kind of throwing these out to expose you to some jargon and so that you can see what the mathematical models look like. And we'll be encountering these a lot. In the discrete time invariant case, we could have something like this, a discrete random walk, which says that the state at time k plus 1 is equal to the state as it was at time k, plus some random white noise. Now here's a wild mathematical example. It doesn't represent anything that you might find in nature or in an engineering project, but this just gives you an example of how wild it could be. The state at times k plus 1 could be the square of what its value was at time k, or k minus 1, times the white noise. So here we have a multiplicative white noise. And the final example is a sort of a typical autoregressive difference equation input. So x at time k plus 1 is equal to a, some coefficient a times the value of the state at time at k, plus b at x k minus 1, and plus some additive noise as well. And if these things were vectors, then they would get even more complicated. Here's a two-dimensional example where you've got a matrix, a constant matrix, driving the state or multiplying the state, and we driving it with white noise. So this would be like a constant coefficient differential equation driven by white noise. In a discrete case, but time varying, you might have something that looks like this. You could have a matrix with some sinusoidal cosines and sines in it that are dependent on k, so this is going to be changing with each value of k. Also, you've got a k squared term there, so there's further explicit dependence on time. And then the white noise added. So this is a difference equation, but with time-dependent coefficients driven by noise. Now let's talk about a real physical example that'll make a lot more intuitive sense than perhaps these abstract mathematical models. Suppose you have a car that's moving in one direction along a road at constant speed and it's under cruise control. So we want to model its position and its velocity because it wants to control the velocity and keep it going at constant speed. And so the two variables, natural variables for the state would be the position, that's what x1 would be, and the velocity, which is what x2 would be. Delta t here is the time difference between the time at k plus 1 and the time at k, and we assume it's constant here. So as you can see here, what we're talking about is defining the position as a function of the previous position plus the velocity and the delta time, right? So distance is rate times time. Note that the position is primarily a function of the velocity, x2, and the time increment, and of course the previous position, right? But there's also some noise terms, and what could these things mean? Well, they could be due to noise due to, say, an inaccurate clock. We don't know exactly whether or not when we take the next estimate based on our clock telling us it's time to do so, we don't know if that's really the exact time, or there might be some error in our clock. Further, we might have in the second variable, the x2 variable, we might have some noise due to some unmodeled short-term accelerations that the cruise control is trying to overcome. So, for example, the road is going to be changing, going up and down, and it's not always perfectly level. There's potholes. And all this is going to show up as some kind of unmodeled acceleration, but they're very short term. So it might make sense to model these with a white noise. Because we've talked a little bit about noise, and since this noise is getting into our differential equations or our difference equations, we need to talk a little bit more about what's happening here. What that means is we're dealing with a random process, otherwise known as a stochastic process. And technically, this means we can't use ordinary calculus to solve the stochastic differential equations. We'll talk a lot more about that later, but just be advised. And one of the properties of these stochastic processes is that when you start with some initial conditions and then let the random variables take on sample values, you're going to get a different sample trajectory every time you do this. And we've actually started simulating that in our Python scripts, and we'll see a lot more of that. So we can take many sample trajectories and simulate them or generate them on a computer using Monte Carlo methods. And then we'll take a closer look at what all this means in terms of random variables and random or stochastic processes once we've drilled down a little bit more in the area of statistics, probability and statistics. We'd like to also mention that we haven't talked about a control function as an input. That could be part of this, and very often in the real world is. Control functions are often considered to be deterministic, even though you can't really control things perfectly. For example, in an aircraft, the actuator, elevator, or flaps, the deflection angle might be a control variable, yet it is very difficult to control it so that you get the actual angular value exactly. There's some uncertainty there. And also we're trying to keep things simple and just focus on state estimation. And so we're going to ignore the presence of deterministic control. And thus the only forcing functions that we'll need to consider in these dynamic models are the uncontrollable disturbance functions we've been calling noise or white noise. And that's precisely what we want to filter out. So filtering is all about separating out the noise and getting the signal. That's why they call it filtering. So what is noise? What do we mean by noise? Well, its key characteristic is that it's uncorrelated in time. So WK and WK plus 1 are statistically uncorrelated as random variables. It means you can't predict what the value of WK plus 1 is going to be from the value of WK. It can only be characterized statistically. Now, process noise is something that's distinct and inherent to the dynamical process and has nothing to do with the actual measurement noise, which has to do with your measurement instrumentation. And so we think of these disturbances as being completely separate and uncorrelated. We'll drill down a lot more on this topic later. When we apply the state dynamics to the previous time step to bring the previous state estimate forward to the present time, we ignore the process noise. And that's because our estimate from the previous time is a sample mean. It's an average, and we expect the noise on average to be 0. We talked about this in the resistor problem. So essentially we can say that x hat minus at time k is going to be equal to the dynamic function possibly explicitly dependent on time, k minus 1, and the last corrected value at time k minus 1 of the estimate. So x hat plus at time k minus 1, but with the noise input being set to 0. So this makes it sort of implicit use of the fact that the process noise is often additive, but certainly that it's 0 mean. The quantity x hat minus k is the basis for the predicted measurement, which results when we apply the measurement function to the predicted state. And we'll talk about that in the next couple of videos. Recall that the prediction step was missing from the running average problem because the f function in that case was a very, very simple identity. Also recall that the measurement function in the running average scenario was likewise the identity function. Although the process noise plays no role in predicting the new state, the process noise statistics plays a very important role in predicting how the estimation uncertainty is going to grow with time. The process noise is also important and is used directly in simulating the system behavior over time, and we'll see that in our Python scripts. And we'll drill down some more on these when we consider the 5 basic Kalman equations in the next couple of playlists. So where are we at? We've looked at some mathematical models of dynamic systems, i.e. models of how the systems change their state with time. We've considered the concept of process noise as a random forcing function, and we've discussed how the state estimate is propagated in time and why the process noise is ignored. So what's coming up? In the next video, we're going to talk about the correction step some more. We were actually dealing with that step in the running average examples, but we're going to talk about it in more detail now. And then after that, we'll talk about the Kalman gain. So that's it for today. Thank you very much. We'll see you in the next video.